Recording now. And let's start. First of all, I'm very happy that you were able to accept our invitation and be here today, Catherine. So today's colloquium speaker is Professor Catherine Espaillat from Boston University. Correct me if I didn't pronounce your surname correctly.
It's Espaillat, but it's very common because it looks okay. French, but it's Catalan, yeah.
Okay, Espaillat. So Catherine graduated from the University of Michigan in 2009, and she then received two back-to-back prestigious postdoctoral fellowships, the first one being the NSF Astronomy and Astrophysics Fellowship, and the second one being the NASA Carl Sagan Fellowship. And during this period, she conducted her postdoctoral research at the Harvard Center for Astrophysics. Catherine then joined the faculty of the Boston University as an assistant professor in 2013, and since 2020 she has been an associate professor at the department. Catherine is interested in the study of young stars, planet formation, and disk structure and evolution. Her research basically focuses on questions like how do planets form and how do the protoplanetary systems evolve. Catherine uses multi-wavelength observations from radio to infrared and optical wavelengths, and she compares theoretical models to data in order to address such questions. During her academic career, Catherine received many honors and awards for her research, including the NSF Career Award in 2015. And she has also been named a Sloan Fellow in 2016, which is quite an accomplishment because it's very competitive. Catherine has also been involved with outreach activities throughout her academic career, trying to promote and mentor underrepresented groups like minority students and women in STEM. So without any further ado, I would like to welcome you, Catherine, and the floor is now yours.
Thank you very much for the invitation. And thank you, Maria, for such a great introduction. You really looked into my past and represented it well. I really appreciate that you took the time to do that. I'm going to be talking today about young 1 million-year-old pre-main sequence stars. They're called T-Tauri stars. And T-Tauri stars are accreting material from their surrounding protoplanetary disks. So here we have an example on the slide of what we think it looks like. Now, simulations predict that the matter accretes from the disk to the star via the stellar magnetic field lines, and then it impacts the stellar surface. And today I'm going to be focusing on that hotspot that forms at the base of these funnels that are slamming material onto the surface of the star. And this is an observable part of the accretion process. And to observe the hotspot on the surface, I'll be looking at multi-wavelength observations of one star and showing you that the observations confirm theoretical predictions that this hotspot on the surface has a density gradient. Okay, so I've divided this talk into 3 questions. So first, I'll discuss what we find in our coordinated multi-wavelength data. Then I'll talk about how we use modeling to conclude that the observed features are evidence of a density gradient in that hotspot on the stellar surface. And then I'll conclude talking about how can we expand this going forward? How can we follow this up? Okay, so first, a very quick background on accretion and how it proceeds in these young systems. So again, we have the young star. It's surrounded by a protoplanetary disk that's made up of gas and dust. And somehow, we're not sure how yet, this material goes inwards towards the star. And then at the point in the disk where the temperature becomes very hot, about 1400 Kelvin or so, it becomes too hot for dust to exist and dust sublimates. And we call that the inner edge of the disk, the inner wall of the disk. And the gas then continues inward because it can't survive at very high temperatures. And it goes inwards until it's truncated by the stellar magnetic field. Now, these young T-Tauri stars have magnetic field strength of about 1 to 2 kilogauss, which should be strong enough to truncate these gas disks. And then the material is channeled via along the magnetic field lines via these accretion flows onto the surface of the star, and it forms a shock as it impacts the surface of the star. And not shown here, on the surface of the star is a hot spot on the stellar surface. Well, here it's shown as a band, but it's actually more oval in shape, and I'll show you examples of that later. Now, observationally, how do we look at accretion in these young systems. So you can see broad emission lines in the optical and the infrared from as the material is going along the accretion flow. And then once the material impacts the surface of the star, it emits very strongly in the NUV, the near ultraviolet, because this is it's impacting the surface at the free fall velocity, and the shock on the surface has temperatures of about 8 to 10 Kelvin. So it emits primarily in the NUV, but there is some emission in the optical. And then I'm not going to be talking about this, but these systems do have excretion from the system. They do have ejections versus via disk winds and jets. So here, I just want to clarify some of the terminology I'll be using because I'm going to be focusing on the hot spot on the stellar surface. And we'll see each of these images later on in the talk, and I'll describe them in more detail there. Here, I'm just giving a quick overview. So here, this is a different schematic showing the disk, the star, and the accretion funnel. That's where it's transferring material from the disk onto the star. So that's the accretion funnel, or the accretion flow. I'll be referring to this as the accretion flow. At the base of the accretion flow on the surface of the star is an accretion column. So this is very close to the surface of the star. And it's here where we have the accretion shock. And I'll go into this schematic in more detail later because we base our model on this schematic. At the bottom of the accretion column on the surface of the star is a hotspot, which is this third image on the right here. So you can think of the hotspot as the footprint of accretion on the surface of the star. And today I'm going to be talking about how we can use UV through optical light curves and variability to learn more about the structure in this hotspot. So the accretion in T-Tauri stars occurs via the magnetosphere, and this has recently been confirmed with spectral interferometry of the closest T-Tauri star, which is TW Hydra, at about 60 parsecs. So there were observations taken of the bracket gamma line, which originates in this accretion flow, and the spectral interferometry places the bracket gamma line as originating within 3.5 stellar radii. And that's well within the 7.5 stellar radii that sets the distance between the star and the inner edge of the disk where the dust sublimates, so that hot inner dust wall. So the fact that the bracket gamma line, which traces the accretion flow, is coming from a very compact area close to the star, and it's not associated with where the bulk of the disk material is further out, that's evidence that it's coming from a magnetosphere and confirms magnetospheric accretion in these young stars. So the details are not clear. And here are some scenarios for how the accretion columns, so as you get closer to the star, the material from the funnel, as it gets closer to the star, we think it gets collimated into an accretion column. Here are some different scenarios for what the structure of that accretion column can look like. So it can have a single density, or it can have a density gradient where it's densest towards the center, or it could actually be multiple smaller columns which each have their own density, or the column can be vertically stratified. Now, MHD simulations of accretion predict that the column should have a density gradient, with the density increasing towards the center, and that you should be able to see this density gradient in the resulting hotspot, because the hotspot is the base of the accretion column. So it carries the density signature of the accretion column. So on the left here, we have an MHD simulation from Marina Romanova, with red representing the stellar magnetic field lines, and the contours are the accretion flow onto the star. And omega is the stellar rotation axis, and mu is the magnetic rotation axis. The middle panel is a top-down view of this simulation, and the disk gas is in green. And then on the right is the resulting hotspot on the stellar surface. And the hotspot is bent around the magnetic pole, and it has stratification in the density. It has gradients in the density, where red represents the densest part of the spot and green is the least dense part. So work has been done in the X-ray previously to try and measure the density of the hotspot using the neon 9 and oxygen 7 lines. The neon 9 line comes from hotter temperature, and so that would be tracing a denser region. And the oxygen 7 comes from a lower temperature, and therefore retracing a lower density. However, the observed X-rays only trace the outermost shell of the accretion column. And so these observations, because they get absorbed, and so the X-rays are not sensitive to the radial distribution of the accretion shock, of the entire accretion shock column. And so, and also complicating things, there is a contribution to these two X-ray lines from the stellar corona. Now, most of the accretion energy that makes it out, that is not absorbed, can be observed in the UV and the optical. And these wavelengths trace most of the hotspot emission. So if you want to learn more about the hotspot, we can look at the UV and the optical. Now, before I show you our data set where we look at UV through optical data of a T-Tauri star, I wanted to show you some previous work looking at accretion variability that motivated us to collect these UV and optical light curves. So T-Tauri stars have been observed a lot in the UV and the optical, and they're known to be highly variable. And we see this variability in the NUV. And this on the left is NUV data highlighted in these gray shaded regions of 3 T-Tauri stars. This was taken by HST, and this is work by Connor Robinson, who's a postdoc fellow at Amherst. And this is the largest NUV variability study to date. And we got observations for 5 T-Tauri stars, 3 to 8 epochs each, spanning the FUV to the near infrared. Here I'm just showing 3 objects. And all of the variability that you see in the NUV, that's variability in the continuum, and that's due to accretion. Accretion variability is also seen in the optical. Accretion dominates the UV, but there's also some optical emission. And these are just 2 objects that were taken to be representative of T-Tauri stars, where their variability was due to accretion variability from a much larger sample of 500 targets in a region called NGC 2264. This was part of the Corot data set and from the YSO VAR survey. And these optical light curves are representative of the kinds of variability seen that are related to accretion variability, where we have stochastic light curves and burster light curves. And these are due to irregular accretion variability. Okay, so now on to the data set that we collected. First, what was the target that we selected? So because of the amount of data we had to get, to do this, we had to pick 1 T-Tauri star. And we chose Gamma Reggi for several reasons. So first, it's a low mass star, and we understand accretion better in low mass stars than higher mass stars like Herbig AABE stars that are more, they're brighter and easier to observe, but we're not sure how accretion proceeds in those systems. It's a transitional disk, and that's what this ALMA image here is pointing to. So it has a 20 AU cavity in the protoplanetary disk. So 20 AU radius cavity. So we didn't want to deal with variability induced by obscuration by dust. So we picked an object that had, these are called transitional disks, that had a big hole in the dust distribution. However, this object is still accreting vigorously, so there shouldn't be any large gaps in the gas distribution of the object. And this object is known to be variable in the NUV. I'll show that in a second. We also wanted an object that had, so I mentioned earlier that these objects emit winds and jets. We also wanted an object that had a detectable jet. Because we also in our study, we not only got UV to optical, we went from the X-ray to the radio. I'll be focusing on the UV to optical, but we wanted to detect the jet and see if we can trace any variability in the jet. And the jet is detected in centimeter images of this object, and that's perpendicular here to the photoionized disk emission that's coming out of the object. And this object has been well studied before by HST, and it's known to be variable in the NUV. So we want an object that we could detect the NUV variability. Okay, so here's an overview of the observations from our multi-wavelength campaign. The observatories are listed here along with the data in parentheses that we got, and then time on the x-axis where we span about a month in time. So we have SWIFT, X-ray and NUV fluxes, HST NUV spectra, Las Cumbres Observatory, Global Telescope, UGRI photometry, TESS optical photometry, Chiron H-alpha optical spectra, ALMA millimeter observations of CO gas lines, and VLA centimeter observations of the continuum. So these data were taken contemporaneously over roughly a month in December 2019. When possible, data were taken once a day. This was motivated by the rotation period of the star, which is 6 days. So we wanted to well sample the rotation period. The test data was taken every 2 minutes. There's a small gap here just due to the momentum dump of the telescope. They don't transmit data here. And the LCOGT data was taken about 5 times per night. And for the rest, it was about once per night. For HST, we had data for about once per night for a week. Again, motivated by the 6-day rotation period of the star. And then any other gaps that I haven't pointed out are due to bad weather or scheduling constraints. Okay, so what do each of these wavelengths cover in the star disk system? So the X-ray emission traces the stellar corona, and I'm not going to discuss the X-ray further, even though there are a lot of X-ray enthusiasts here, because we find no significant variability in the X-ray emission. So it doesn't factor into our analysis or interpretations. And then we got NUV and optical photometry that traces the accretion shock and the stellar photosphere, and we find significant variability, and that's what I'll be spending most of this talk discussing. We got H-alpha data, and that traces the accretion flow. CO emission line from ALMA that traces gas, tens of AU from the star, and centimeter emission traces the jet emission. Now, we didn't find any significant variability in the radio emission, neither the ALMA nor the VLA observations, but this is the first time that radio variability has been studied for T-Tauri stars. So I just wanted to show one slide showing the results of this, even though it was a non-detection of variability. So we observed the common CO tracers, 13CO and C18O. And here we have the C18O line to continuum flux ratios as the points, and then the uncertainties are plotted here. The mean values are the, sorry, this is 13CO and this is C18O. And then the mean values are the solid line, and the mean uncertainties are 1 sigma, and those are the broken lines. And we did some tests with our disk chemistry models, running simulations. You can look at the paper if you're interested. And we find that this makes sense, that in order to see an increase in the UV luminosity and also the X-ray luminosity, if we use changes in the UV luminosity and the X-ray luminosity that have been observed for GMRIG in the past, we would not be able to detect this variability with in the disk with current facilities. We would need a burst, a large change in the UV and the X-ray emission that lasts about 100 years. And that's implausible in the T-Tauri star phase. That could happen in earlier stages like the FUR stage, but not at these later stages that we're looking at here. And then for the centimeter continuum emission, that's shown in the bottom panel, same lines as the top two. And we saw no discernible changes outside of the uncertainties. And so we conclude that changes in the mass loss rate, which are being traced by the jet emission, they're not large enough to be detected with current facilities. Okay, so now let's talk about what did vary and what we can learn from that. So in the next few slides, I'll show that there are 2 observed features in the UV and the optical light curves. So first is there's a time lag between the peaks in the UV and the optical light curves. And then the second is that we have a dip in the UV and the optical light curves at the same time. And I'll show you using models and theoretical simulations that both are evidence of a density gradient in the accretion hotspot. Okay, so here are the NUV through optical light curves of GMRIG. From top to bottom, we have SWIFT, LCOGT, U prime, G prime, then we have TESS, then we go back to LCOGT, we have R prime and I prime. The uncertainties here are smaller than the symbols, and the bandpass of TESS covers the bandpass of both R prime and I prime. So we see, when you look at the light curves, that changes appear, daily changes appear, and there's a period of about 6 days. And this is consistent with a 6.1 day rotation period of the star. And that's evidence of rotational modulation. So there's something on the surface of the star that's coming into and out of our view. And I'll show you, we think that this is a hot spot. All right, so if we put, we see a time lag between the UV and the optical light curves. So here the red shaded boxes are overlapping peaks in the UV data and also the G light curves. And each of the red boxes are separated by the rotation period of the star, so about 6 days. And then if we do the same for the optical light curves, but in the green shaded boxes below, you see that those boxes are shifted to the right and they're tracing the peaks in the optical light curves. So it's interesting that we're seeing that the optical light curves are offset by a day from the UV light curves. Now, this can be explained by density structure in the hotspot. So material slams onto the star, leaves a hotspot on the stellar surface. The UV emission traces the high density region of the spot, which is in red, and the optical emission traces the low density region, which is here shown in green and blue. And as the star rotates, we see different density regions of the hotspot as it goes into and out of view. And the time lag between the peaks and the UV and the optical light curves, this is the first observational evidence that we have of a density gradient in the hotspot on the stellar surface. And I'll just show that one more time. And I'll show more of the simulations later so you can visualize how this is happening. Okay, next. Okay, so then the second feature we see, aside from this time lag, is a dip. And it happens in all the light curves at the same time and is highlighted here in gray. And it occurs on December 23rd to 25th. And there's another dip on the 21st to the 22nd, but it's very short. And we only see it in the test data. It's so narrow, it's so short that we weren't able to catch it in any other of our data sets. We just didn't have observations at the same time. So we only catch it with tests. Now, the second dip, we do see it in tests, but we don't see the whole thing with tests. But we do see it in the other light curves. We see the entire dip. And geomorphic does not have, like I said, it has a big hole in the dust distribution. So it doesn't have any significant dust in the inner disk. So these dips are not due to dust extinction. Now, what's interesting is that these dips are followed by the disappearance of the UV peaks in the light curve. So you see some peaks before, and then afterwards, they're no longer present. But the optical peaks appear to remain here. So what we think this is telling us is that this is also due to a density gradient in the hotspot on the stellar surface. The high density part of the hotspot is expected to be very unstable, and so it can disappear. And so it could be that that there was a decrease in accretion, leading to this decrease in these dips in the light curves, and then afterwards, the UV peak, the high density part of the hotspot went away. It became unstable. So this could be tracing instability in the accretion process. Okay, so we talked about two observables, the time lag between the peaks and the dip in the light curves. Both can be explained by a hotspot on the stellar surface with a density gradient. And I'll show you now how this is consistent with accretion shock modeling and MHD modeling. So first, I'm going to show you that accretion shock modeling finds that the UV light curves are dominated by the high density part of the hotspot, and that the optical is dominated by the low density component of the hotspot. So here's the schematic that I showed you before. So we have the accretion shock model of Calvet and Goldbring, which is used in this work. And this is the schematic that it's based off of. And this consists of a vertical accretion column, and it's close to the surface of the star, constrained by the stellar magnetic field. And it's divided into three subregions: the pre-shock zone, the post-shock zone, and then the heated photosphere below the shock. And here we have the shock. And then the top of the accretion column is met by that funnel flow, that arc that connects the disk to the star. And the base here is the accretion hotspot on the stellar surface. It's not shown here. So the accretion shock, the accretion column generates emission in the NUV and the optical, but where the emission peaks depends on the density of the material. So on the right, we have simulated light curves created by Connor Robinson that use the accretion shock model. And this is coming from 3 accretion columns, assuming that they have 3 different densities, which correlates to energy flux. So red is the highest density accretion column, and you can see it peaks at shorter wavelengths. And then purple is the lowest density accretion column, and it peaks at the longer wavelengths in the optical. Okay, so here I'm showing, so this is a busy figure. What this is showing is the 5 epochs that we have of HST data, HST NUV spectra, and the modeling that was applied to them. In the next slide, I'll show you what we extracted and compared to light curves here. I just want to show you the actual modeling. The HST data are in black. The best fit total model is in red, the solid line. And that red solid line, the model is composed of adding a template photosphere, which is the broken blue line. And that's what a weak T-Tauri star that is not accreting, what its photosphere looks like. And then you see all this excess emission that's coming from accretion. And then the other lines that you see here are the broken lines. So we have a high density column in red broken line. We have a medium density column, the broken gray line, and low density column is the broken green line. And so we add up these different density columns, which are representative of having a density gradient in the accretion column and then the resulting hotspot. And then from these models, we extract the properties of the accretion column and the hotspot. So here we're interested, and I'll show you the next slide. We're interested in total energy flux of the columns, the hotspots, the density, and also the size of the hotspot. Okay. So here we're taking the model's properties of the hotspot and comparing them to the light curves. And here we're focusing just on the week that we got HST data. So in the top panel is the test light curve during that 1 week that we got HST data. And then we have here U prime. This line here, I mean, these points here are the total energy flux of the hotspot. And yes, and what you can see is that when the U prime data peaks, the total energy flux of the accretion column and the high density region and the hotspot are the high density region of the hotspot are the highest. So what this bottom panel does is it breaks down the energy flux into high density region of the hotspot versus low density region of the hotspot. So the high density region are the circles, and the low density regions are the triangles. So you can see that the total energy peaks with the U band, and then the red, the high density region, the circle, the contribution from the high density region also peaks with the U band. So this is showing that the UV emission is probing the high density part of the accretion hotspot. And you can see that it drops significantly after December 8th. And so that means we interpret that as it's rotating out of our view. Okay, and then here we have the same, the top 2 panels are the same as before, but now we're looking at the size of the hotspot here. So this is the total size of the hotspot. And then here we have on the bottom, the fraction of the hotspot that is covered by the high density part of the hotspot, which are the circles, and then the low density. So what this is showing is that the hotspot is dominated in spatial distribution by the low density part of the hotspot, so that the high density part is very small, and that that emission peaks along with the test, the optical light curve. So showing us that the low density part of the accretion of the hotspot is dominating the emission, the optical, and that's what's peaking with the optical light curve. Okay, so that was showing us how the accretion shock models focusing on the HST data to get the properties of the hotspot, the density from the hotspot, and then comparing it to light curves and seeing that high density region of the hotspot dominates the UV, and the low density region of the hotspot dominates the optical. Now we're going to look at MHD simulations of accretion, and the MHD simulations show that we would expect a time lag in the light curves, and also that we would expect that the emission from the high density part of the column will go away over time because of the instability in the hotspot, in the highest density portion. So first, let's go through the simulation setup before we start comparing to our observed light curves. So we use the 3D MHD simulations of Marina Romanova, and these are of a rotating magnetized star accreting from a disk. And the models assume that the star has a dipole magnetic field. The rotation axis of the star is omega, and the magnetic axis is mu. And the angle between these two, which is often called the misalignment angle, is theta. That's not written out here, but it's going to come up later. And this is a 3D view, a side view, and then a top-down view. And then here is the hotspot that results from this particular configuration at this particular time. And the hotspot is crescent-shaped. It's bent around the magnetic pole, and it has a density gradient. So red is densest, green and blue is the least dense. Okay, so that's the MHD simulations of accretion. Then we have to get the observed parameters of G-Maraghi in order to compare to so that we can have the simulation that's closest in some parameters to that of G-Maraghi. So and MHD simulations take months to run, and we wanted to publish this as soon as possible. So we went through the simulations of Lanova et al. 2015 and picked out those simulations that had the parameters most similar to G-Maraghi. So the MHD simulations show that the properties of the hotspot depend on theta. Again, that's the misalignment angle, and the magnetospheric radius. So that's the size of the magnetic field. So the theta of G-Maraghi is 13 degrees, and that comes from McGinnis et al. They measured the hotspot of G-Maraghi to be at a latitude of about 77 degrees. And they measured from the amplitude of the radial velocity, variations of the helium-1 line, and they took into account the star's projected rotational velocity, b sine I, and they were able to derive theta. So the misalignment angle, they found it to be 13 degrees. And then to get the magnetospheric radius, remember we got Chiron optical H alpha spectra of G-Maraghi. Those are the data here in black, and the red are best fit models of using accretion flow models. So with this schematic here, and from those models, we can measure our magnetospheric radius. And we measure that magnetospheric radius is about 4 stellar radii. So we can use that to go through the simulations and pick out the ones that are closest to G-Maraghi. And here, the MHD simulations I'm showing you in the next few slides have a theta of 20 and an RMAG of 4.5 R star, which are consistent with the observed parameters of G-Maraghi. Okay, so the MHD simulations can explain the time lag between the UV and the optical light curves, and also the drop in the UV emission. So here we have stimulated light curves generated by different parts of the hotspot, where the solid line is the low density region of the hotspot, and the broken line is the high density region of the hotspot. Both of the light curves are modulated by the stellar rotation period, and the high density region of the hotspot rotates out of view, which leads to a time lag. And here, that leads to a time lag between the light curves, and the UV peaks before the optical. So you can see this at 3 R star. You can see that there's a time lag between the light curves, and you can also see this at 5 P star, the stellar rotation period. You can see that there's a time lag between the peaks there, and the position, shape, and the structure of the hotspot varies with time, and this influences the high density part of the hotspot, and it causes it to occasionally disappear, and therefore the emission from the low density region of the hotspot persists, but the emission from the high density region of the hotspot can disappear. And that happens here at 2 P star. and also at 4 p star. You can see that the high density component goes away. So this right panel here, it focuses on one of these peaks, the peak around 3 p star. I'm going to step through these now, so it's a little bit easier to compare the 3D simulation here to a hot spot here to the light curve. Okay, so this broken line here corresponds to 2.6 p star, which is, and this is the emission you get from the light curve here, from the hot spot here. I'm just going to step through these. Here we have 2.69 p star, which is the next line. And then we're adding the next one at 2.77 p star. And then here you can see that you see all of the high density and low density part of the hot spot, but the high density part is directly along our line of sight. So its emission peaks first. And then here again, you see all of both. And here you're starting to get that the high density part is getting farther away from our line of sight. So its emission is decreasing, while the larger portions of the low density part of the spot are directly along a line of sight. So now its emission is peaking, the low density part. And then here you start to see that both are rotating out of view. So you see that both in the light curves for both, the emission is decreasing, and then even more is hidden. And then very little of the hot spot. Okay, so where do we go from here? So there is a lot of potential for accretion variability study of T-Tauri stars in the near future. Variability in general, but I'll be focusing on accretion variability. Okay, so the HST director approved a discretionary UV legacy program with 1,000 orbits to obtain UV spectra for pre-main sequence stars and high mass stars in a program called ULLYSES. And this is the largest HST program ever executed at 1,000 orbits. And half of that allocation is to study 70 T-Tauri stars. And half of that 500 orbits, 100 orbits in particular are being used to monitor 4 T-Tauri stars for variability. And Geomorrhagi is one of those 4 targets. And the ULLYSES program is so important that has unified the T-Tauri star community into a team called Odysseus. Our team is made up of about 75 young star experts from around the world, and we're going to bring together our combined knowledge to work collaboratively on the ULLYSES data. And our team's goals are to study the accretion flow, to study winds and jets, and to study the FUV radiation field. So we just put out a paper with our first results. And just to show the wide range of data that we can collect by working together. And we have HST spectra up to a 1 micron in black, the similar as I showed you before with the weak T-Tauri star here and the accretion shock model fits. So this is coming from ULLYSES, and then the rest of this data over here is coming from the Odysseus team. So we have X-shooter data, optical and near-infrared spectra. That's over here. And then we have multi-band light curves. They're being collected by all these different facilities over here. There's also TESS, which is the solid black line in this panel here. And we have several papers in the pipeline that will be coming out this year. So stay tuned for that. Including papers coming out on those 4 monitoring targets. So the data for the monitoring targets, they're going to be visited 2 times, separated by about a year. And the first set of data is in for those 4 targets. And then the second set, it will be actually TW Hydra, one of the 4 targets. It's going to be starting up this week, the second round of observation. So that data will be in by the end of this year for all 4. All right, so just to summarize, the UV and the optical light curves of Geomorrhagi, they have periodicity separated by that agrees with the stellar rotation period, but they don't peak at the same time. And so there's a time lag between the UV and the optical. We interpret this as due to a hot spot with a density gradient. So we have different density regions of the hot spot that emit at different wavelengths. The high density region of the hot spot emits in the UV, the low density part emits in the optical. And as the hot spot rotates on the stellar surface, at different times, we see different ratios, different amounts of the high density spot versus the low density spot. And that's what leads to the offset in light curves. And these observations confirm theoretical predictions that the hotspot should have a density gradient, and it demonstrates what we can get from coordinated multi-epoch, multi-wavelength observations. And this also shows the possibilities that we have for future progress in the field of time domain studies of T-Tauri stars, and the importance of getting coordinated multi-wavelength data whenever possible, because it's very hard to get this data. But it also gives us a lot of insight, and it's a unique opportunity to get these multi-wavelength data sets. So there should be a lot of activity in the T-Tauri star community on variability in the next couple of years with all of this ULLYSES data that's coming in, so stay tuned. So thank you very much for your time, and I'll take any questions that you have.
Thank you very much, Catherine, for this very interesting talk and for giving us this nice overview about T-Tauri stars, combining data with theory. So I think we have plenty of time for questions, and I would like to encourage everybody to unmute themselves and ask directly Catherine their questions, or if they cannot unmute themselves, they can type their questions on the chat. It usually takes some time just to, to start asking.
Maybe I
have a very different research area.
I have a question. It's not a question, if I may.
Yes, of course.
Thank you very much. Very clear talk. Not too many questions. One or two points maybe I have missed. When you say about high and low densities, actually you mean a gradient, and it's not that you have in your models a high, it's like a step function. It's a continuous gradient of the density, if I understand correctly.
So yeah, that's a good point. So the expectation is that there is a gradient, and that's what the MHD simulations show. For what they use for the accretion shock models that I'm using, it is a step function because we don't have we haven't revised the models yet to take into account a density gradient in the hotspot. So there we do have high density and low density, and they're separate, and there's no gradient in between the two in the accretion shock model, but we're using that to try to reproduce the data, and it does a decent job roughly. But in the future, we will be introducing a density gradient there.
Okay, thank you. And earlier you showed some radio observations talking about the jet. This radio observation is, what's the origin of the emission? Is it like a non-thermal radiation, or it is some kind of, I don't know, thermal wormstrahlung or something?
Yeah, let me go back.
You had the disk and the jet.
Yeah, I know this one, right?
Yes.
So yeah, so here, okay, so there's two different kinds of emission that are coming from the centimeter. So there's photoionized emission coming from the disk. And then there's also jet emission. And these are high resolution images taken with the VLA of G. And so these two can be distinguished. The photoionizing radiation, which should be related to high energy radiation like the X-ray photoionizing the disk. And then the jet should be tracing accretion. Now, our observations that we took of G with the VLA were in the low resolution configuration of the VLA. So we got all of the emission. We didn't get any spatial resolution. So we got both the jet and the photoionized disk. But the X-ray emission didn't change. So we have no reason to think that the photoionizing disk emission changed. So if we had detected any kind of variability, we would have been able to attribute it to the jet. So yeah, so the radio emission that we're tracing is a centimeter with the VLA that's coming from photoionization and also the jet for this particular object.
Okay, thank you.
You're welcome.
Are there any other questions? So I'd like to ask one till the rest think of any questions they have. So I would like to ask about the magnetic field and how of the accretion column, and if this enters into the calculation of the radiation that you showed us. So I was wondering, if the magnetic field strength comes into play. And second of all, like the second question, which is related again, is, are you also planning in the future to study more complex magnetic field topologies for these stars with simulations? And if so, how, are you thinking of using exactly the geometry of the hotspot just to figure out what the topology of the magnetic field in these young stars is?
Yeah, so for the first question, we don't, the strength of the magnetic field doesn't factor into the accretion shock model that we're using. We just assume that the column is constrained by the magnetic field. So that doesn't factor into the accretion shock model. For the MHD simulations, the strength of the magnetic field, I think in marina simulations, the strength is tied to the accretion rate. So that's tied up in there. Now, so the MHD simulations do take into account the strength of magnetic field via the accretion rate that's used. And the accretion rate of G Maraghi is about 10 to negative 8 solar masses per year, which is pretty typical. And the accretion rate of the simulations that I showed was about 10 to negative 8 solar masses per year. So a typical accretion rate, a typical magnetic field that we would expect for a T-Tauri star. So going forward, so as part of Odysseus, there are some observations that are being planned with Spiru, coordinated in time with the monitoring sources by the teams that have access to the facility to look at, can we get more information about the magnetic field along with all of the other data that's being taken. So this G Maraghi data that we had, we didn't have any observations of the that would help us constrain the magnetic field, but those observations should be taken, should have been taken for the 4 monitoring targets and are going to be taken for the first set of the 2, and then they will be taken for the second set of the 2. So we will have some information on the magnetic field topology, what we think it looks like. And this is being led by the Donati group and Bouvier, who do a lot of work in this region, in this area. So that'll be really exciting to see how the magnetic field, like if it's changing and how it's changing along with the accretion variability. So I think, so does that answer both of your questions?
Yes,
okay.
It does. Thanks.
Welcome.
Please do not hesitate to ask questions. I don't see any hands raised. I think it was I see one, but I think it was a very nice and clear talk. So, George?
Yes, thank you very much for the very detailed talk. So I mainly work on accreting magnetized neutron stars, so I see lots of similarities, and I have like trying to make some analog models or have some questions. So I'm curious, like, one thing I see also from this slide is that the size of the hotspot is like comparable to the size of the star, like it's a fraction of its radius. And I'm quite used, like in neutron stars, it's only a couple of meters, like 100 meters in a 10-kilometer radius, or in a double degenerate white dwarf system, it's again like a very small fraction of the white dwarf radius. So is this mainly due to the fact that the disk is truncated very close to the star in this case? Like in the slides in the left, that you mainly go up to 3 times the radius of the neutron of the star, so you get like accreting material in a wider range of the surface. And
yeah, I mean, I would have to look into the. I would have to look at the papers and refresh my memory. I think it is related to the magnetospheric radius, how big the hotspot should be. I do have this slide where we infer so this is not the same as the MHD simulation. This is the accretion shock model, and it's telling us what fraction of the stellar surface is covered. that we're looking at. And here it gets up to about 20%. And that's based on the observations where we're comparing the emission, excess emission above the stellar photosphere, and then we have the weak T-Tauri star template, how much emission do we expect from the photosphere itself. So yeah, so observationally, yes, it's about 20% of the half of the star that we're looking at. So it seems like a lot. And then for the MHD simulations, I have to dig into the papers and see what parameters that's.
So, and this measurement has only been done in such detail. It has been done only in this star, or is there like estimates on the coverage fraction for multiple stars? Or
yes, there is. So this is the only star that's been done at multiple wavelengths with this amount of data over a month. But there are lots of studies of T-Tauri stars, lots of observations of the hot spot, and as part of, lots of measurements. And as part of the ULLYSES work, one of my grad students is looking at eventually what will be 70 T-Tauri stars and using these accretion shock models. And one of the parameters she's looking at is the size of the hotspot. So we will have more statistics on the size of the hotspot from modeling the NUV in the near future. But no, GMRIV isn't the only one. It's just the only one we've been really focused on, where we got a lot of data.
Okay, thanks. That makes sense. So it's something to hope for the future.
Yeah, and then we'll see how big this hotspot gets.
Okay, so has any other person thought of a question or something was not clear and would like to ask our speaker to clarify? I have one question again, which might be a little bit naive because I'm not an expert on that. I was wondering about the magnetic activity of these stars and whether or not, definitely this, I'm not aware of the timescales that the magnetic field might change on the stellar atmosphere or stellar surface. So I was wondering if with these observations, at least you are also planning or hoping for searching for these effects of magnetic activity in these young stars.
Yeah, so from what I know about the magnetic activity, the weak T-Tauri stars, the ones that aren't accreting, they have a lot of, so if you're saying by magnetic activity, looking at cool spots on stars, they have a lot of variability from cool spots. For the accreting stars, it's hard to see variability from cool spots because it's the light curves are dominated by the accretion hotspots because they're very hot. But there should also be some variability induced by cool spots on the accreting stars. So yes, there are ways to look at the magnetic activity through looking at the behavior of the spots on the stellar surface. And we have all these light curves now. TESS is coming out too. So there should be a lot of information coming out soon about that, but I'm not aware of right now if there's been anything definitive, if we can link that directly to like magnetic field strengths or anything like that. That's outside of my area of expertise, those details.
Okay, thank you. Yes, I don't see any other questions. So I think it's time perhaps to close our meeting for today and thank Catherine once again for joining us and giving us this very nice overview talk. So yes, there are clapping hands, virtual clapping hands. Okay, so thank you, and we will resume in 2 weeks from now. Okay, have a good day.
Have a good day. Thanks for the invitation.
Thank you.
Thanks. Bye-bye.